So today, numerical analysis. So let's go slowly. And maybe, so what we've seen from up till now was everything with the generator. Hello. Great. So I thought the point of today would be to give an idea of how numerical analysis works. Go from the basics till the basics of stochastic numerical analysis. So in numerical analysis today, we begin with ODEs. And so you take an ODE that is of the forms y prime of f of y t plus an initial condition y0 to y0. You say that the words are in t in 0 t. And what we usually do is that we apply discretization of 0 t. So we have then is equal to nh, where h is called the time step, or step size, or whatever. There's a lot of names for this. And we have t 0 is equal to t0, this is equal to tn, capital N. So you have nh is equal to capital T, and you have 1, 2, 3, 4. And so the point is to approximate y of tn at each step. And you have plenty of ways to study it. So the first thing is that you would like to get something of the form. Well, let's present an example. So this is other method given by yn plus 1. So the approximation of y of tn plus 1 is equal to yn plus h, the step size, times f of yn. So it's often criticized in the literature because it's the crappiest method, it's the easiest one, but it's not really the easiest one. Another method that would be much easier would be yn plus 1 is equal to 0. That's easier. So in a way, the Euler method is the easiest non-crazy method. And by non-crazy, I mean it's consistent. So this consistency means that yn plus 1 minus yn divided by h actually converges when h equals to 0 to maybe for only one step. That's called consistency. I don't like y0 minus x. Nah. Okay, this is true for every way. So what this means is that first, this limit exists. So it means that y1 is close to y0. And it means that you approximate the solution of the equation at least for the first order. If you write a Taylor expansion, you approximate the term of order 0 and order 1. That's what I mean by non-crazy method. So this is an important problem. The point is that, again, the Euler method is the first, the simplest, the crappiest, non-crazy method, but it's also the least expensive. So when you have an application, you have to get the most accurate method, the most stable method, a method that preserves the geometry of the problem, but also it has to be not that costly. So you have to find where you want to start. So I like to think of this as a metaphoric sense. So this is a triforce of numerical analysis. It's accuracy, this is here, We want to be very accurate. I will define what it means too. And you want to be stable. That is, if f is a crazy function that has a coefficient 10 to the 6, for instance, and a very small coefficient in it that is 10 to the minus 6, for instance, the method should not explode, which does not mean it's accurate, it's just stable. And then we have the last part of the try first, which was forgotten for a long time, and that appeared again when they studied when we wanted to send some men to the moon, because the method the physicists were trying to find explicit solutions of the way to go from an orbit around the Earth to an orbit around the moon, for instance, and this is impossible in most cases. So they had to rely on Untitled methods that were old at this time. So they found again the Euler method and all these things, and they wanted a method that behaved in a good way in long sum, and this calls for geometry property. So that's when it appears again. So the most famous book in numerical analysis, called Geometry and Numerical Integration, begins with a quote that is, they threw geometry out of the window and it came right back at the door because we had to study it. Even if we don't like geometry, we actually have to study it. It's so important. So now,
So the question,
yeah.
why this one is defined with the new formula here? So y1 minus y0 divided by x is always equal to f.
Yes, I am for any method, not for this one.
Okay.
For any method. So another example of method, that is a generalization of the Euler method in Untitled Chapter. So you have substages yi is equal to yin, and we often forget the n, is equal to yin plus a sum of ni. And yn plus 1 is equal to yn plus a sum bi s. See, that seems a bit crazy. We went from something very simple, that is just a truncated Taylor expansion, to something completely crazy. So another example of something you could take, and then I will come back to this, is just a truncated Taylor expansion. So let's do it together. We have y of h. Let's do it for one step. Y of h equals to y0, so y prime of 0 times h plus h squared over 3 y second of 0 plus all right, this is just Taylor. Now y prime of 0, we know what it is. We just have to evaluate this equation at times t equals 0. So it's f of y0. Right? Now, this is a bit harder. You have to differentiate this equation. So you have y second of t is equal to f prime of y of t in direction y prime of t. And then you replace again y prime by f plus f prime of y of t times f y. So here we can just replace that by f prime of y0 times f of y0. And then, well, you could say, I define my method as y minus 1 equals to yn plus h f of yn plus h squared over 2 f prime of yn of yn. And this is a method that seems accurate, and I can do this for any order. And why the heck am I going through the trouble of defining this when I can do something as simple as just truncating a Taylor expansion? Well, there are no reasons. Hi.
That's good.
We're still talking about the basics of numerical analysis, then I go to test. So the point here is that this is very annoying. You don't want to compute everyone. If you work, for instance, in molecular dynamics, you have you work in dimension 10 to 24 ideally. Computing a Jacobian matrix of size 10 to 24 times 10 to 24 requires heavy symbolic calculus that we don't have. So this is impossible. And so the reason why you need these kind of methods is to avoid using derivatives that you don't have access to. And that's why we don't just calculate their expression. Also, this is very unstable in practice. So this is just focusing on this, and then we forget about the cost of geometry and stability. Anyway, that's very example of this. And so there's a theorem. By the way, it becomes stochastic in like 2 minutes. Okay, so it's the theorem that will prove the stochastic setting. It's just the idea that you should keep in mind is that if you have a method that is accurate and stable, perfect. Okay. So one thing that I forgot to say is that these three errors that I presented, if you have a method of strong order P, it has at least weak order P. If you have a method of weak order P, it has at least order P for the normal measure under reasonable assumptions. So strong methods are the strongest, but they cost a lot. And you can find some very cheap and surprising methods for the multi-measure that have order one, weak order one, I mean. So you can really pay whatever you want to approximate, and it's worth asking yourself the question, what do I want to approximate? This is very cool. Anyway, so let me recall a few assumptions that we did along the way, and then we will be ready. So the equation we studied is dx equal to f plus dt plus g of x dw. F and g are Lipschitz, which in particular implies that f of x is less than or equal to 1 plus x. Let's simplify it, and g of x is less than or equal to 1 plus x, blah blah blah. They're also smooth. And we take test functions in 5 in C infinity. So I have to give this full explanation. It means that for whatever k, the partial derivative of order k of 5, any derivative of 5, satisfies an inequality of the form C 1 plus x to k. And C and k depend on k. Okay? It just means that phi and all its derivatives have polynomial growth. It will just be used once. Let's forget it. Okay. So the proof, as I did for the ODEs, is split into 3 parts. The first part is stability, the second part is accuracy, and the last part is convergence. So we will begin with the demo. If expectation of x0 is less than infinity, then application of xn is less than 0. And xn is given by the Euler method that I should write somewhere. xn plus h f of xn plus horizontal h j xn. Okay, so let's prove this one. You see that this stability is the same way that we presented earlier. It means that, this, it means that xn cannot approach. But we have to take all models. Okay. So let us first compute expectation of xn plus 1 minus xn, knowing xn. So I say that xn is equal to x. Okay. And I suppose that xn is fixed. So this is not random anymore, this is not random anymore. Only random part of this is this one. So you have expectation of h f of x, right? Plus square root of h g of x sine n. But it has average 0. So the expectation of sine n is 0. It's just a Gaussian law. So what you get is h expectation of f of x. So less than 0.2, yeah. And with this, it's less than h c of x. Okay. That's one. Second inequality, we look directly as xn plus 1 minus xn, and we bound everything. So what we get is, yeah, it's c1 plus xn, that is bound f, multiplied by square root of h, with the h, sorry. So this is for this term. And the other terms is 5 plus c, 1 plus xn, multiplied by square root of h times sine n. So in practice, what you have is c, 1 plus xn, square root of h, and something else. And then we'll go mn. This is my number 2. All right. And this has, this mn satisfies this equation. It has all the moments of full order because it's just the Gaussian law. There's no problem. So section, I will write g delta xn is equal to xn plus 1 minus xn. Then xn plus 1 to the power 2m is going to be 20. Is xn plus delta xn to the m. I use Newton's formula, so xn to the m plus 1, and the binomial coefficient 1 into m, xn to m minus 1, delta xn, plus the sum of j over 2 into m of j n, and delta 1 j delta xn. Just tweaking what the same in any dimension. You just have to do this for every coordinate. Okay, this is number 1. This is number 2. This is number 3. Number 1, I will keep it. And number 2, I will take the expectation of this. So I have the expectation of this thing, xn square minus 1 delta xn is less than, so I can just write this expectation of the expectation. Right? That's how we define the conditional expectation at the very beginning of the course. It's still the same quantity. Then this, we've computed it here. So we'll use this inequality. And I have expectation of xn to the square minus 1 multiplied by h here and 1 plus x. So 1 plus x. Okay. And so in the end, I get something of the form constant by h times 1 plus 50% of xn. Okay. With number 3, I do the exact same thing, but I use this inequality instead of this one. So I have multiplication of xn to m minus j delta xn to j is less than or equal to xn to m minus j multiplied by delta xn. This we know from here, this is exactly delta xn is less than something with bounded moments. So when I take the expectation, I have this C H, because it's root of H times to the power at least 2, then 1%, and then you have Mn that has bounded moments. So in the end, you find C H 1 plus expectation of Xn. Because Mn power was less than, it's just a constant, completely independent of it. So in the end, what we've proven is that expectation of xn plus 1 to the power 2m is less than, I want to write the mistake, so 1 plus the constant times h multiplied by the expectation of xn, right? So this one comes from this term, and from this we've got this kind of estimate here that gives us this, the h. So this I can just multiply by exponential h, and then I can just get the exact formula with the deduction. So I have expectation of xn less than exponential c h to the n times the expectation of x0 to m. This is less than 2. This is less than constant. And this, by the assumption, is less than constant. Okay. This is stability. And this seems like a very annoying proof. It is very annoying. But if you look at papers doing stability assumptions, like explicit stabilized methods for stochastic differential equations, for instance, that's the tricky part. We're doing this. This is very standard. This is not doing this because it's very known. This is very standard. That was the first part, stability. Now we have accuracy. This is the part I prefer. So, you know, we want to approximate expectation of phi after one step. We just do one step of the algorithm. So what we want to approximate is the expectation of phi of x of p, which we denoted as u of x0 h. And we said that u of x0 h, u of xt, actually satisfies u of xt equal to nu. Right? So actually from this, I say that u of xh satisfies u of x0 plus h n of x. and you basically make okay, fine. And fine. Okay, so okay, this is voltage 2. This is not precise, but it's not worse. What we want is order 1. So this is the Taylor expansion, or at least the equivalent of the Taylor expansion for the exact solution. So we would like to do the same with the numerical approximation to get the Taylor expansion and to show that they match. Okay. So what we want to prove is the following. Okay, is that expectation of phi of x1, so I just do one step of the method, minus this here, phi of x plus h and phi. It's less than or equal to CH2. So of course this is not enough. We don't have this big O or H2. We have something else. It's CH2 multiplied by 1 plus x to the n. We have regularity properties. We have to take care of some assumptions. So that's what we have. Just to get to everything. So that's what we want to prove. And to do this, we write this quantity, expectation of phi x1, and we replace x1 by its definition. So that's expectation of phi of x plus h of x plus h of g of x. This is the definition of the Euler method. Okay. Now this is annoying, so I will just do a Taylor extension of this in phi. As expectation of phi of x plus also h phi of x multiplied by g of x psi plus h phi of x x plus 1 time by second. See, this is annoying because I want anterior expansion in h, but then I have a term of size 1/2 and anterior size 1. So I put some terms of quadratic just in the h term, so it's kind of annoying. By second of x, direction each side. Plus something. Okay. Now, don't let these complicated terms fool you. Everything is linear, so this is just this term, and I take the expectation. It's just this term multiplied by expectation of psi, and expectation of psi is 0. So this term is 0, and I take the expectation. Now we're left with the last one. So that's phi of x. We assume that the initial condition is deterministic, so it's just phi of x. Then this is also deterministic. I will drop the x. And this, by definition of the expectation, it means that I have to take the components, it's 0 unless I take the same components of sides here and there. So what I get in the end is going to add the sum to I to k of phi second g. And by GO, I mean this. This is 1 plus x. And this is exactly m. This is the sense. This is eventually. It's the expression of that. So I have phi of x plus h and phi of. So we proved this.
We can also have the term in h to the power of 3 halves. We also have the expression of the terms equal to 0.
Yeah, exactly. That's why a method has we order an integer and never a half, unless you do crazy things. But anyway, we don't do crazy things here. So that's the local accuracy. So what we said, if you haven't, I just want to remind you of how numerical methods work. You have your curve, you begin here, that's x0, then you have x of 1, x of 2, blah, blah, blah. And what we did is that we said that we're accurate up to one step. So basically, we know how to estimate this. The problem is that then we did the one step here, and not from here. Then we do like that. So we know how to estimate that. And when we apply the algorithm several times, we don't start from x of t1, we start from here, and then we start from here, hence the stability property. As long as this does not explode, when you compare with x of t2, this will know how to control it. So we need the last step to combine the accuracy here, the stability, and to prove that this is close to this. Okay. Ready? This is the hardest part of the proof. The point is that in for SDEs, we like this. For SDEs, we go backward. So everything will be very annoying if I'm doing the exact same proof as for ODE. It's just much more difficult. So I will write xxt is the solution at time t starting from x. And we have x and x, which is the end step of the numerical algorithm that starts from x. Right? And what I mean from x is that at t equals 0, x0x is x. Okay? Okay. So I write p is equal to expectation of phi of x n. Minus phi of s and x. This is my goal. I want to bound this bit. And I want, the thing I have is the error of the one step. So I want to go backwards. So what I do is I write this telescopic sum. Expectation of phi of x starting at xn minus phi of x of minus phi. It's a telescopic sum. You agree on this. Then you only keep the first and last term. The first term is the last term is x n minus n. So that's x0. x0x is just little x, and so I get this term. Yeah. With I is equal to 1, in this term I get xn minus 0. So it's a solution, the exact solution at time 0. So the solution time 0 starts from here. It's just this, which is f. No problem. we have still the sum, and I will try to make the local approximation appear. We have expectation of 5, okay, x, and minus 5x of h. I promise it's not that hard. Just have to go slowly. Minus expectation of 5 of x1, x, and minus 5x. I'm sorry. So, what happened? I just decomposed everything. So this xn minus I plus 1 can also be written as I apply one step, and then I apply n minus I step, which is exactly what I wrote there. Right. The first term, though, is that I start here. I say that the exact solution at time ti is the exact solution at time ti minus 1, and then I make a step h. Right? And that's what I do. I start at time ti minus 1, and I take a step h. That's all I do. Okay. Now I define phi tilde is phi of x equals phi composed with the exact solution. You believe me, it's a test function and will not prove it. It's not that hard, it is moving, so believe me, it is infinity. Right? Then I can rewrite all of this as the sum of I equal to from 1 to n of expectation of phi cubed I of x and minus 5x minus expectation I x 1 x minus 5. And this very much looks like a local error, like in just making one step and comparing two steps with weird initial conditions, with a weird test function, but still I'm just comparing one step as a exact solution against one step of numerical method. So what we get from what we've done earlier, we know that this is less than or equal to the sum of now I have to do it here. Of expectation of c h squared multiplied by 1 plus a polynomial in the initial condition. Right? So this is the local approximation that we've done earlier, the accuracy, the local accuracy. And now we're almost done. So this is equal to c h squared 1 plus the expectation of x n minus 5 x. Now we use the stability to say that this is a constant. It does not explode. This is the thing we proved at the very beginning. The method does not explode. So this is less than constant. Sorry. So this is just C N H. This is what we define as T. So it's very technical. And you see that we went backwards. What we really wanted is to make this appear, because now we're just comparing one step of the method and of the exact solution. And once we have this, it's all a question of stability. Like this step is to say, my method will not explode, and then I get my estimate. What time is it? Yes, Good. So this is what I wanted to do today. I wanted to do a bit more, but I think we should stop soon. I want to talk about what will happen next time. So maybe next week, January, we will do it. I don't know. Maybe it will be me. The point now is that now that you know how it works, how this proof works, we can actually adapt it for all classes of methods. So I will not do the proof again. You are convinced now. But the point is, I will focus on the accuracy. So what we see that if you have some accuracy that is local, if you have some stability, then you get a convergence. If you have all the P of accuracy, then you get convergence of all the P. And the point here for the next sessions will be to try to make higher methods first, to see how we can do the computations effectively and to adapt during from the ODE case. And then we will talk a bit about geometry and constraints and how to make a method satisfy the same properties as the solution. But I think I don't have time, so I will just stop here. Questions?
When you remove stability, I think I was thinking that.
Yeah, okay, that's fine.
Sorry.
It's not-
You must have assumed something about your driving vector field.
Yes, but they are Lipschitz.
Which
I mean, a lot of things exist, especially when you're starting to look at equations like this. There's F epsilon. Okay, let's just do it like that. Find the widely picture of this. But the point is that in real life you have equations like that with parameters epsilon and eta in the equations. So I'm just taking a very small example here. But if epsilon and eta go to 0, then you would like your stability property to be also independent of epsilon and eta.
yeah, they go to 0, they write other together.
Yeah, okay, so there exists some some people manage to do this. Okay, for Langevin, for instance, let's take Langevin. So you have minus W dt plus sigma W, and you can add a penalization, something like minus 1 over epsilon, a function, use of x, and level theta x. And you can show that if epsilon goes to 0, then this has to be 0. So when epsilon goes to 0, you have theta x epsilon goes to 0. So that is x epsilon, and the limit epsilon goes to 0 goes to a manifold that satisfies something. But anyway, if you apply all the method to this, it will explode badly. So there's a whole part of the literature, it's stochastic, that focuses on multi-scale stochastic methods to find clever numerical methods that whose stability typically and accuracy does not depend on epsilon, which is very hard, but anyway. So these you have two sets of methods. You have asymptotic preserving and uniformly accurate. Some people focus on having a convergence result when epsilon is fixed and when epsilon goes to 0. And the best you can have is uniformly accurate. It is the cost and accuracy of the method is completely independent of epsilon. And then the stability property becomes really hard to prove. It takes pages and pages. We won't do that. We will not do it. It's just too hard and beyond the scope of the course. Questions? Then let's go to coffee booths. We have a great cake from Hans today, right?
Yes.
Fantastic. Let's do that.